Look at a modern AI output, and you see a perfectly coherent, professional result. Because it sounds confident, we grant it excessive reliance. But inside that polished answer, we find a brittle foundation built on unverified assumptions, conflicting constraints, and probabilistic guesses. This exposes the difference between capability and authority. Capability is strictly what a model can do: its reasoning accuracy, the tools it can call, and the length of its context window. But high accuracy alone cannot determine whether a particular output has the structural authority to be trusted in a high-consequence situation. Correctness is not trustworthiness. An AI can arrive at the right answer through an entirely unreliable reasoning path. This is why the energetic paradigm shifts the focus of AI governance. We have to move away from evaluating a model's global reputation on benchmarks and instead govern its localized operational reliance. We can measure this shift by looking at an AI's operational space. First, there is raw freedom, the total number of actions technically available to an unrestricted autonomous system. Then there is effective freedom. This is the much smaller subset of actions an AI can execute without breaking its goal constraints, outrunning its evidence, or transferring uncontrolled consequences to users. If we only govern an AI's capability by slapping static access filters on its raw freedom, we leave it structurally dangerous. To make autonomous systems viable, trust must be engineered as an active control state. This diagram shows a standard multi-agent architecture. Ingestion, synthesis, and execution are handled by separate autonomous nodes. Right now, a data packet sits at Agent A. Agent A detects a potential supply chain delay in the data. It flags the issue, but correctly assigns it a very low confidence score of 30%. But watch what happens during the data handoff. As Agent B summarizes the report, the confidence metadata is sheared off to save token space. This specific systems engineering failure is called epistemic inflation. In autonomous chains, unverified possibilities naturally solidify into absolute facts simply through repetition and the loss of context between agents. Now we trace that degraded packet to Agent C. Because the uncertainty data is gone, Agent C interprets the summarized possibility as a critical, verified failure and executes a catastrophic capital rerouting. Notice the paradox here. No new evidence was introduced into the system. The system's operational momentum alone manufactured a confident, destructive action. Standard static permission models, like role-based access control, are completely blind to this. Agent C had the permanent technical access to move capital, but no mechanism checked if it still had the authority based on the degraded state of the data. This exposes the flaw in relying purely on a human in the loop. A human reviewer, given only a final approve or deny prompt, lacks the context to see the original low confidence score, rendering their review purely ceremonial. Static permissions and ceremonial human reviews ignore the degradation of reasoning paths. Autonomous systems require active authority controls that scale directly with real-time evidence. This hub illustrates the energetic paradigm's solution, the trust architecture. It requires 6 structural transformations to prevent epistemic inflation. Transformation 1 moves from global reputation to local reliance. Action authority must be granted dynamically, based purely on the current state of evidence, rather than how often the model is historically correct. Transformation 2 moves from evidence display to evidence control. Just showing citations is insufficient. A drop in evidence quality must mechanically contract the available action space. Transformation 3 shifts from verbal uncertainty to an operational control state. When a model indicates uncertainty, it cannot just generate a textual caveat. It must trigger a hard mechanical stop. Transformation 4 replaces ordinary data transfer with trust-preserving handoffs. This is known as path governance. Data handoffs between agents must rigidly transfer the assumption constraints and uncertainty metadata. If that context drops, authority is revoked. Transformation 5 moves from ceremonial approval to explicit trust authorization. Escalation paths must transfer the true consequence architecture and the full context to a human sovereign. It cannot just ask for a blind click. Transformation 6 moves from incident recording to trust reconfiguration. Failures cannot just populate a log file. They must trigger a structured repair process that permanently alters the system's future authority thresholds. Collectively, these 6 transformations turn trust from a subjective feeling into a hardened engineering constraint that actively regulates system momentum. Now let's apply the trust architecture to the original multi-agent failure. The data packet moves from agent A to agent B, and its confidence meter begins to dissolve. Generative models are structurally biased toward continuation. Once prompted, they generate. Therefore, the architecture must actively intervene using the safe stop flow. Step 1 is suspend. The system immediately halts the action that has lost sufficient authorization, rather than pushing through just to produce a complete-looking hallucination. Step 2 is expose. The system highlights the exact threshold failure, identifying precisely where the uncertainty metadata was stripped. Step 3 is preserve. All relevant state data, intermediate work, and failed assumptions are saved into a sandbox. This ensures the next reviewer does not have to rebuild the context from scratch. Step 4 is escalate. The preserved context is routed directly to an authority level, human or institutional, that possesses the actual jurisdiction to accept the consequence. Step 5 is repair. The resolved event alters the system's reasoning path, ensuring that this specific loss of context cannot repeatedly trigger an unauthorized action attempt. A truly governed AI proves its intelligence not by aggressively pushing through to an answer, but by knowing exactly when its authorization no longer supports its next move. This scattered field represents an AI's total raw freedom. But the objective of AI governance is not maximal restriction. A completely locked-down system produces 0 operational value. The energetic paradigm's true objective is maximum useful freedom. Maximum useful freedom is the largest action space an AI can inhabit while maintaining goal alignment. This boundary is highly dynamic, expanding outward where evidence is rich, but it rapidly contracts around high-consequence, irreversible nodes, forcing escalation to a human sovereign. While the proprietary mathematics governing these precise expansions and contractions remain undisclosed, the public architectural necessity is undeniable. Raw capability will always produce answers, but action authority dictates whether those answers have the right to alter the real world. The future of autonomous systems relies entirely on converting unchecked intelligence into legitimate action. We must give AI the stable structure it needs to survive in high-stakes environments.